August 1943, Tillamook, Oregon, the edge of the Pacific. The man standing at the open end of the structure did not move for a long time. Lieutenant Commander Harold Briggs had seen aircraft hangars before, the sprawling steel sheds at Pensacola, the squat concrete buildings at Corpus Christi. He had an engineer's eye, trained to reduce large things into their components, load-bearing walls, roof trusses, compression ratios. He knew how to measure a building by the math behind it. He could walk into almost any structure and within a few minutes understand the logic of how it stood. None of that prepared him for this. It can't be wood. It can't. The thought arrived not as a question, but as a refusal, because the structure rising before him, filling his entire field of vision from left to right, from earth to sky, was not what a wooden building was supposed to look like. It was not what any building was supposed to look like. 51 curved arches swept upward from concrete pads in a parabolic arc, each one made of layered Douglas fir glued and bolted into a single laminated unit, ascending 192 feet to the ridgeline, the height of a 17-story building. The arches marched along the full length of the hangar, one after another, like the ribs of some impossibly immense whale, stretching 1,072 feet from the open end where Briggs stood to the far wall he could barely distinguish in the distance. 3 football fields, more than a fifth of a mile. And every timber, every rafter and crossbrace and truss member, every ridge board and diagonal purlin and connector block was wood. Wood. In a war that ran on steel. Inside the hangar, 8 K-class blimps floated at their mooring lines. Their helium envelopes stretched 252 feet from nose to tail. Crewmen moved below them on the hangar floor with the unhurried efficiency of men doing familiar work. Inspection circuits, valve checks, the 1,000 small tasks that kept the ship's flight ready. They looked, from Briggs's position at the entrance, like ants crawling across a vast gray tundra, dwarfed into insignificance by the geometry that surrounded them. 2 interior catwalks ran the length of the building at a height of 137 feet, high enough that the men moving along them were barely distinguishable. The nearest arch rib was close enough for Briggs to rest his hand against the laminated fir, to feel the slight roughness of the wood grain under his palm, and to feel beneath that the almost imperceptible vibration of the building breathing in the wind off Tillamook Bay. This was Naval Air Station Tillamook. It had been built from the first stake driven into an Oregon dairy farm meadow to the final panel bolted down on the roofline in less than a year. One of 2 such hangars constructed here, one of 17 such hangars across the entire country. In 1942, with the nation bleeding ships off both coastlines and steel rationed to the last girder, the United States Navy had done something that every conventional military engineer said was flatly impossible. They had commissioned the largest clear-span wooden structures in the history of human construction, and they had built them in months. But there it was, proof that changed everything. If you want to see how this incredible feat of engineering defied expectations and shaped the war, support us with a like. It helps us uncover more buried stories like this. Subscribe if you haven't already. Now back to why these colossal structures were so urgently needed. The arches creaked faintly as a gust moved through the open doors, each of the 6 door panels per opening weighing 30 tons, the full door assembly rolling on rails into hollow enclosures built into the concrete pillars at either end. Outside, somewhere beyond the fog draped over the Pacific, enemy submarines were hunting. There was a reason these structures existed, and that reason was written in fire and oil on the surface of the sea. The journey to that Oregon dairy meadow had begun 13 months earlier and 3,000 miles away in the cold waters off the American Atlantic coast. When German Vice Admiral Karl Donitz dispatched his first wave of 5 Type 9 U-boats toward the American coastline in December 1941, he expected resistance. He got essentially none. The U.S. Navy's Atlantic coastal defense consisted of 7 Coast Guard cutters, 4 converted private yachts, and a scattering of First World War vintage patrol vessels with neither the speed nor the armament to reliably threaten a modern submarine. More critically, the American merchant fleet continued to sail individually, unescorted, with navigation lights burning, against the illuminated backdrop of resort towns that refused wartime blackouts for fear of damaging the tourist trade. Atlantic City, Virginia Beach, Miami. Their lights blazed every night above the sea lanes, as if no conflict had ever reached their shores. The German submariners could scarcely believe what they found. Kapitän-Leutnant Reinhard Hartigan, commanding U-123, made landfall off the American coast on the night of January 12, 1942, the first of the Drumbeat boats to reach its assigned patrol area. What he found stunned him. Ships sailed past in clear silhouette against the shorelights, running their navigation lamps on peacetime schedules, following established peacetime routes. No air patrols, no surface escorts, no blackout. The entire eastern seaboard had simply not yet adapted to the reality that the war had arrived at its doorstep. Before exhausting his torpedoes and making for the French port of Lorient, Hartigan sank 9 vessels totaling more than 53,000 tons of shipping. Among the German submariners, the sentiment spread quickly. The Americans, they said, were offering a shooting season. The other 4 boats of the first Drumbeat wave confirmed it. Ernst Kahls in U-130 sank 6 ships of 36,988 tons. Robert Richard Zapp in U-66 accounted for 5 ships totaling 33,456 tons. Heinrich Bleichrodt in U-109 sank 4 ships of 27,651 tons. The 5th boat, U-125, under Ulrich Folkers, sank only 1 vessel and was criticized by Donitz upon return to port for his poor performance, though the single sinking he achieved would have counted as a successful combat patrol on any other front of the war. Off Cape Hatteras, North Carolina, where the Gulf Stream pushes north and the shipping lanes compress against the Diamond Shoals, conditions were so favorable that the merchant mariners who survived their attacks gave that stretch of coast a name, Torpedo Alley. Sunbathers at Virginia Beach watched 2 ships go down within sight of the beach on a single afternoon in June. Locals along the Florida coast reported that the flames from burning tankers were bright enough to read by at night. Korvettenkapitän Peter Kramer of I-333, surfacing off the Florida coast after darkness to ventilate his boat and charge batteries, would recall the experience vividly after the war. His crew emerged from the conning tower into a peacetime landscape, buoys blinking, lighthouses sweeping, a famous hotel's neon sign casting a pink glow across the water, while somewhere within that glow a tanker was burning. The official American designation for this phase of the battle, Operation Drumbeat, made it sound controlled and tactical. What it was, in practice, was the worst naval defeat the United States had ever suffered on its own waters. By the end of May 1942, the toll stood at more than 360 merchant ships and tankers, totaling roughly 2.25 million gross tons, sunk between the Gulf of Mexico and the Canadian Maritimes. Nearly 5,000 merchant mariners were dead, most of them on ships sunk in sight of the American coast. When the second happy time finally ended around August 1942, the result of convoys, coastal patrols, and sheer Allied urgency, 609 ships had been sent to the bottom. That figure represented roughly a quarter of all Allied shipping destroyed by German submarines during the entire war. The Pacific coast faced its own reckoning, arriving without warning 13 days after Pearl Harbor. On the afternoon of December 20, 1941, the 6,912-ton oil tanker SS Emilio was running south from Seattle toward San Pedro, California, when the Japanese submarine I-17 surfaced 20 miles off Cape Mendocino. 5 shells from the submarine's 14-centimeter deck gun struck the tanker in rapid succession. Captain Clark Farrow immediately ordered "abandon ship." The Emilio's radio operator managed to transmit an SOS before a shell destroyed the antenna. 3 crewmen were killed attempting to launch a lifeboat. 2 engineers died in the engine room when a torpedo struck below the waterline, The remaining 31 survivors drifted in lifeboats for 16 hours through a driving rainstorm, navigating by dead reckoning, before finally reaching a Coast Guard lightship anchored in Humboldt Bay. The Amidio herself drifted unmanned northward, eventually grounding on rocks off Crescent City. Her rusted bow section would eventually be listed as a California historical landmark. It was the first attack by Japanese naval forces on a vessel off the California coast. Japanese submarines were already operating throughout the Pacific approaches, and their doctrine differed from Donitz's Atlantic campaign. Imperial Navy submarines were tasked primarily with attacking warships rather than merchant vessels, prioritizing tactical military targets over the tonnage war. But the effect on shipping movement was the same. The lanes from San Diego to the Strait of Juan de Fuca were now contested waters, and no one defending them had any way to watch the surface of thousands of square miles of open ocean continuously. In Washington, the strategic problem was newly urgent on both seaboards simultaneously. The sea lanes required persistent aerial patrol, surveillance that could detect a periscope cutting the surface at 3 miles, that could hold station over a convoy for hours rather than minutes, that could operate in the Pacific coastal fog and low cloud that grounded conventional aircraft for days at a stretch. The Navy knew what platform could do that work. The question was whether they could build enough of them, and whether they could build the infrastructure to sustain them. In early 1942, the Navy's inventory of K-class patrol airships stood at 6 operational blimps. 6. The entire American coastline waited. The K-class blimp was not a glamorous weapon. It never appeared on recruiting posters or featured in newsreel footage the way fighters and bombers did. No one wrote popular songs about it. The men who flew them were Navy aeronauts in an age when naval aviation meant aircraft carriers and torpedo planes, and the lighter-than-air community occupied an awkward corner of the service, associated in the public mind with the Hindenburg disaster of 1937 and with a technology that seemed, to most observers, like a relic of the previous war. Those observers were wrong in an important and specific way. The K-ship measured 252 feet from nose to tail and 80 feet across its helium-filled envelope. It was non-rigid. The envelope's shape was maintained by the internal pressure of the gas rather than by an internal frame, which made it lighter and simpler to maintain than its rigid predecessor airships had been. 2 Pratt & Whitney R1340 Wasp radial engines, each developing 425 horsepower, drove the ship at a cruising speed of 50 to 67 knots. The 40-foot control car slung beneath the envelope carried a crew of 10, 2 pilots, a navigator, a radio man, 2 mechanics, and ordnance men who maintained the weapons load, 4 325-pound depth charges, and a pair of .5 caliber machine guns in the forward positions of the car. An ASG surface search radar with a range of roughly 90 miles was mounted in a radome on the car's exterior. Magnetic anomaly detection equipment, capable of sensing the disturbance caused by a steel submarine hull in the Earth's magnetic field, gave the crew another tool to locate submerged contacts below. The total endurance of a fully fueled K-ship reached 48 hours in normal operations, enough for 2 full crew rotations during a long patrol. That endurance was the tactical advantage that no other aircraft could replicate. A destroyer escort moving at 20 knots spent perhaps 30 minutes in the visual range of any given position in a convoy's path before passing out of effective protection distance. A land-based patrol plane like the PBY Catalina, flying at 120 knots on its patrol circuit, swept through a search sector in minutes, enough time to spot a surfaced submarine, not nearly enough to pursue a contact once the aircraft had overflown the target area. The K-ship could reduce its speed to match the convoy's pace of 8 or 10 knots and simply stay there hour after hour, scanning the surface with eyes and radar while the depth charges waited in their racks. The submarine commanders adapted quickly to the presence of patrol aircraft, which could appear without warning and be gone before a U-boat crew could even finish their dive. Against the Blimp, that adaptation failed. The K-ship could observe a contact, reported by radio, call in surface escorts, and maintain visual surveillance of the position simultaneously. It could wait out a submerged submarine for hours, hovering over the last known position, making it impossible for the contact to surface and run on diesel power without exposure. The patrol record that ZP-21 Squadron out of Naval Air Station Richmond, Florida, achieved later in the war measured this directly. At least one K-ship aloft continuously, without interruption, 24 hours a day, 7 days a week, for 965 consecutive days, from the squadron's operational establishment through the final days of the war. Not a single ship was lost to submarine attack in a blimp-escorted convoy, ever, across the entire war. This record generated some scholarly debate after the war. The convoys also carried surface escorts, and disentangling which deterrent mattered more was impossible from the outside. But the German perspective on the question was unambiguous. Post-war interrogation of senior U-boat commanders, including Dönitz himself, consistently cited lighter-than-air patrol as one of the most effective Allied defensive countermeasures. When a U-boat captain could not surface to run his diesel engines for battery charging without risking immediate detection, his operational range collapsed to what his batteries alone could provide. The blimp overhead turned the Atlantic coastal approaches from a killing ground into a trap. But to make any of this possible on the scale the situation demanded, there needed to be 17 of these hangars, and the Navy needed them within the year. In the spring of 1942, the original construction plan met an obstacle that no amount of urgency could simply override: steel. There was none to spare. The Navy's pre-war planning for a coastal, lighter-than-air network assumed structural steel construction. The Bureau of Yards and Docks held preliminary specifications for steel-framed hangars within the established vocabulary of industrial construction. Large, certainly, but achievable. Bids were solicited. Drawings went out. Work was expected to begin in 1942 on a 10-base network stretching from New Jersey to Southern California. Then came July 3, 1941, and the second deficiency appropriation bill. The legislation placed strategic materials under federal allocation control, with steel foremost among them. Each Liberty ship required roughly 3,000 tons of structural steel in its hull and frames. Destroyers, carrier frames, artillery pieces, tanks, the weapons of a military expanding at a pace the world had never before witnessed, consumed material at a rate that left nothing for construction programs that could be built another way. The hangar program could not have steel. The directive came down without ambiguity or appeal. The engineers began working through alternatives. Reinforced concrete could handle compression loads, but behaved poorly under the dynamic wind forces that a structure of this size on an exposed coastal site would experience. And concrete rebar was steel anyway, just in a different form. Aluminum was already fully committed to aircraft manufacturing. The Army Air Forces had first claim on every pound produced. The remaining candidates narrowed quickly. Wood had been the structural material of American construction for 3 centuries, from the timber-framed buildings of the colonial era through the great covered bridges of the 19th century, where multiple smaller members connected into a truss geometry had allowed spans far longer than solid timber could achieve. But the spans that worked for a covered bridge were measured in tens of feet. The Navy needed a clear interior span of 296 feet, the minimum width to accommodate multiple K-ships moved laterally without any internal columns breaking the floor space. The ridge height needed to exceed 175 feet. The structure had to withstand the full lateral wind loads of an Oregon Pacific coastal site, sustained over decades. No timber building in American history had approached those requirements. The man the problem landed with was Arsham Amirikian, principal engineer of the Bureau of Yards and Docks. Born in 1899 in Kaigi, Armenia, Amirikian had received his early engineering education in Constantinople and then at the École Nationale des Ponts et Chaussées in Paris, before coming to the United States in the early 1920s. He received his degree in civil engineering from Cornell University in 1923, then spent 5 years in private practice working for steel fabrication shops, learning the material's behavior and bolted and riveted connections from the fabricator's side of the table. In 1928, he entered government service as an assistant structural engineer at the Bureau of Yards and Docks. Over the following decade and a half, he published more than 100 technical papers and articles, established himself as an authority on the structural behavior of timber, reinforced concrete, and steel, the full vocabulary of modern construction materials, and advanced through the Bureau's grades to the position he held in 1941 when the Blimp hangar problem arrived at his desk. There were no guidelines, no precedent, no data. Every previous air dock built in America or Europe had been steel-framed, and the engineering community had accumulated a century of knowledge about steel's behavior under load. Wood was different in its properties, more variable, less predictable at extreme scales, with structural behavior that had never been measured at the dimensions the Navy's specifications required. Amirikian approached the problem from first principles. The catenary arch was the key insight. A catenary describes the shape taken by a hanging chain or cable, the natural curve that gravity imposes when a flexible medium supports its own weight. When inverted, that curve becomes a compression arch, and a compression arch has a distinctive structural property. At every point along its profile, the load resolves into pure compression along the axis of the arch, with no bending moment. In a conventional beam or a flat truss, loads generate bending moments that must be resisted by the upper and lower chords of the structure, creating high stresses in the material and requiring greater material depth to resist them. In a catenary arch, under its intended loading, no bending moment exists. The material is loaded entirely in compression, the direction in which timber, like stone and concrete, performs best. Amirikian designed a system of 51 such arches for each hangar, spaced 20 feet apart along the building's length, each arch assembled from hundreds of individual Douglas Fir boards laminated together with waterproof synthetic resin adhesives and fastened with steel ring connectors and through bolts at the connection points. No single piece of lumber in any arch was particularly remarkable. The available timber supply in the Pacific Northwest ran to standard milled dimensions, and the wartime disruption of rail and labor supply made exotic custom cutting impractical. But assembled into a catenary profile, with the geometry doing the structural work that the individual boards could not do alone, those ordinary boards became something that had no precedent in American construction. A quarter-inch scale model was constructed to test the structural theories before any building material was committed. Engineers loaded it, studied the deformation patterns under various load conditions, and adjusted the arch geometry and secondary truss spacing to confirm what the calculations predicted. The model matched the analysis. The design, once issued, varied remarkably little from what the test had shown. Amirikian brought the arch bases down to grade on concrete bent frames, massive poured concrete foundation elements that transferred the arch thrust forces directly to the ground. Between consecutive arches, a secondary system of purlins and cross-bracing tied the structure into a rigid three-dimensional whole, preventing the individual arches from buckling laterally under asymmetric wind loads. At each end of the hangar, 6 massive sliding door panels hung from rails and moved laterally into hollow pocket enclosures built into the terminal concrete pillars. Opened fully, they provided an aperture 220 feet wide and 120 feet high, sufficient to admit 3 K-ships simultaneously side by side. The design completed review in the autumn of 1941. Engineering News Record, the construction industry's most authoritative journal, would later call Amirikian's wooden hangar the most outstanding structural development of the wartime period. Ground was broken at the first sites almost immediately. The construction timeline that followed was not a concession to urgency, it was urgency itself, made physical. At Tillarook, Hangar B began in October 1942. A brutal Oregon winter followed, with November delivering 18.5 inches of rain and December delivering over 19 inches. Work did not stop. It could not stop. The crews worked in the rain, raising the arch rib sections by derrick crane, splicing the prefabricated laminated components at their field joints, advancing from foundation to ridge line in sequences that had been worked out from the model and the drawings. Hangar B was complete on August 15, 1943, 10 months of continuous construction in one of the wettest coastal climates in the continental United States. With the engineering problem solved and the supply chain established, Hangar A went up in 27 working days. 27 working days for one of the largest wooden structures ever built. Not because the workers were extraordinary, no serious injuries or deaths were recorded on the entire Tillamook construction project, but because Amirikian's design had been tested and confirmed, and every crew on site knew exactly what came next. The same plans were building hangars simultaneously at Lakehurst, New Jersey, at Elizabeth City, North Carolina, at Weeksville, North Carolina, at South Weymouth, Massachusetts, at Glencoe, Georgia, at Richmond, Florida, at Houma, Louisiana, at Hitchcock, Texas, at Moffett Field, California, at Tustin, California. The coastal air shield was rising out of the forests of Oregon and the pine stands of the southeast, arch by arch and purlin by purlin, while the U-boats still hunted. To understand why the wooden hangar program worked as well as it did, delivered on schedule, built without catastrophic failure, still standing in some locations 80 years later, requires understanding what the designers were actually trying to solve. The requirements for each hangar were not arbitrary. They derived directly from the dimensions and operating characteristics of the K-class Blimp itself, and from the physical realities of keeping a non-rigid airship in service. A K-ship inflated and ready for flight presented an envelope 252 feet long and 80 feet in diameter to the handling crew on the hangar floor. It came in tail first along the long axis of the building, guided by ground crew holding handling lines at the nose and tail. The ceiling of the hangar had to clear the top of that inflated envelope by a sufficient working margin that inspection crews could move along the upper surface during servicing, hence the interior height requirement of more than 170 feet at the ridge. The width had to permit lateral parking of multiple airships side by side with the clearance margins that safe ground handling required, hence 296 feet of clear span. The length had to accommodate a full squadron with room for mooring equipment, maintenance facilities, and access for the door trucks and equipment handlers. Every dimension was a derived requirement. The architecture followed the aircraft. The answer to those fixed requirements turned on one engineering decision: the use of glued laminated construction rather than relying on mechanical fasteners alone. Conventional heavy timber framing transferred loads between members through bolts, lag screws, and metal connector plates, discrete contact points through which compressive and shear forces passed from one piece of wood to another. This worked well at the spans used in warehouses and barns, where the connections carried manageable forces and the deflections under load remained within the range that bolted joints could tolerate. At the scale of an arch spanning 296 feet in the clear, the forces at every connection point were in a different category entirely. Under the cyclic loading of Pacific coastal winds, sustained gusts, turbulence from the door openings, the differential pressure created when a 30-mile-per-hour gust struck one end of a 1,000-foot structure while the other end remained calm, bolted connections would work and relax thousands of times per year. Over time, they would loosen. The structure would develop play. The geometry that the arches depended on for their load-carrying behavior would begin to shift. Glued lamination solved this. Waterproof synthetic resin adhesives, a technology available in industrial quantities only in the late 1930s and early 1940s, bonded the individual fir boards into a continuous composite section. The adhesive layer between adjacent laminations transferred load in shear across the full bond area rather than through discrete fastener points. The assembled arch behaved structurally as if it were a single piece of wood far larger than any tree could have produced, with none of the fatigue vulnerability that bolted connections introduced. The ring connectors and through bolts that remained in the design were there to reinforce the field splice connections between arch sections, the joints that had to be made on-site rather than in the fabrication shop, not to carry the primary structural loads. The laminated sections were fabricated in regional shops and trucked to the construction sites as finished components. This meant that the most demanding part of the construction process, assembling individual boards into the arch geometry under controlled conditions, applying adhesives at the correct temperature and pressure, curing the bond before load was applied, happened away from the coastal sites where weather was a constant adversary. By the time an arch section arrived at Tillamook, the structural work was done. The site crew assembled pre-made components. Here is the central truth of Amirikian's achievement. This was not wood used as a substitute for something better. This was wood used as the optimal material for a specific set of constraints, selected on engineering grounds rather than in desperation. Steel would have been faster to design. The industry had a century of data on steel connection behavior. But fabricated steel components in 1942 required mill lead times that ran to 18 months or more through facilities already committed to Liberty ships and Sherman tanks and B-17 structural members. No amount of contract priority could accelerate a steel hangar fast enough to matter. Timber, by contrast, was available in the forests within 50 miles of every coastal site on the program. The lamination technology was new but accessible. The construction trades that could work with wood existed throughout the Pacific Northwest and the American South. American industrial genius in the Second World War is usually told as a story of mass production. The River Rouge plant, the Kaiser shipyards, the Willow Run bomber factory. Those stories are true and important, but they are stories about exploiting abundance. The wooden hangar program was something different, a story about what happens when a brilliantly trained engineer applies the same analytical rigor to scarcity and finds that the constraint produces a better answer than the abundance ever offered. The Blimp fleet that took up residence in those hangars flew patrol missions along American coastal waters from the Gulf of Mexico to the Pacific Northwest, beginning in late 1942 and running through the final days of the war. The operational impact accumulated gradually, then all at once. For the merchant sailors running in coastal convoys, the appearance of a K-ship overhead changed something that the raw numbers don't capture. The ships carried general cargo, steel, rubber, oil, ammunition, food, in runs that traced the same lanes the U-boats had hunted so freely in the first months of the year. The escort destroyers and submarine chasers could protect the flanks of the convoy, but they could not see below the surface, and they could not be everywhere simultaneously. The Blimp could do neither exactly, but it could maintain a continuous watch from 300 feet up over a column of ships stretching 3 miles, scanning the water with its radar and its human eyes for anything that did not belong. A white feather of water at periscope depth, an oil smear from a damaged ballast tank, the slow, spreading circle that marked where something had been submerged and was not anymore. One account from a merchant officer on the Atlantic run in the spring of 1943 describes the convoy forming up at dusk off Cape Hatteras, the destroyers taking position on the flanks, and then a K-ship moving up from the south and taking station above the column's center at about 400 feet. His log entry for that night noted that the Blimp was still there when he came back on watch at 0400. It was still there when he went below again at 0800. The convoy completed its run without incident. That without incident is the hardest thing to quantify in a war record. The absence of an event, a torpedo that was not fired, a submarine that chose not to attack, a U-boat captain who decided that the presence overhead made the approach too unfavorable, leaves no entry in the casualty lists and generates no battle report. What it did generate was a pattern, and the pattern was unambiguous. The ships that moved in Blimp-escorted convoys did not get sunk. On July 18, 1943, the limits of that protective equation were tested from the other direction. K-74 was flying a routine night patrol above the Florida Straits, southwest of Key West, when its ASG radar returned to contact. Aviation machinists made Garnet Eckert, scanning through the gondola windows, spotted a surfaced U-boat silhouetted in the moonlight at roughly a half-mile distance, U-134, running on the surface to charge its batteries. Standing orders for K-ship crews encountering a surfaced submarine were explicit: establish radio contact, report the position, maintain observation, and await surface units. Engage only in self-defense. Pilot Nelson Grills pressed in for a direct attack. U-134 turned hard and opened fire with its 20mm deck guns. A burst tore through the K-74's gas envelope, releasing helium and beginning the slow deflation that would eventually bring the ship down. Aviation machinist's mate Isidor Stessel managed to release 2 depth charges in the attack run. They fell close aboard the submarine but did not hold the pressure hull. The K-74's starboard engine caught fire, and the ship came down in the water, the crew surviving the ditching and spending 8 hours in the warm Florida Strait waiting for rescue. 9 of the 10 crew members were recovered. Stessel, who had waited in the water longest, was taken by a shark in the minutes before the rescue craft arrived. It was the only combat loss of a K-class blimp to enemy action in the entire war. 1 aircraft, 1 crewman dead. U-134 reported the engagement to U-boat command as a minor victory. It was not. The damage from Stessel's depth charges, assessed as light at the time, was apparently sufficient to compromise the submarine's diving capability. U-134 was located by a British Wellington bomber of 179 Squadron in the Bay of Biscay on August 24, 1943, 5 weeks after the Florida Straits encounter, attempting to reach Bordeaux on the surface, unable to submerge. The Wellington's depth charges sank her with all hands. The K-74's crew had done their job before their ship came down. The U-boat that killed one of them never made port. Back on the Pacific coast, the squadrons flying from the wooden hangars at Tillamook and Tustin conducted continuous watch over lanes that ran from the California border north to the Canadian Strait of Juan de Fuca. Squadron ZP-33 at Tillamook operated 8 K-ships across a 500-mile operational radius, covering the shipping approaches to Portland and Seattle. The K-ships at NAS Tustin, which became operational in October 1943 after a construction sprint that began in April 1942, patrolled the Southern California approaches, the San Pedro Channel, where the Pacific Fleet's logistics trains moved, and where civilian shipping served the industrial ports of Los Angeles Harbor. The Pacific coast threat was Japanese rather than German, and it differed in character. Imperial Japanese Navy submarines emphasized warship attacks over merchant tonnage, which limited the magnitude of shipping losses but not the danger to naval vessels operating in coastal approaches. The blimp patrols kept those approaches under watch that no other platform in the Navy's inventory could sustain. The fog that rolled in from the cold California current every morning and sat over the coastal lanes until noon was no obstacle to a K-ship's radar. It was an obstacle only to the fixed-wing aircraft that might otherwise have taken some of the patrol burden. The cost of achieving that coverage was, by the arithmetic of the wartime Navy, remarkably small. 17 hangars, 134 blimps, 1 aircraft lost in combat. Not 1 ship lost in an escorted convoy. By 1943, Axis submarine attacks on American coastal waters had dropped to 65 sinkings. The following year, that number reached 8. The wooden arches were holding the line. The hangars. 17 LTA timber hangars completed across 10 naval air stations, 1942-1943, each measuring 1,072 feet long, 296 feet wide, and 192 feet tall, with an interior floor area exceeding 7 acres. Lumber consumed per hangar. Sources report between 2 and 3.3 million board feet of Douglas Fir, supplied by up to 50 regional lumber companies per site. Steel saved per hangar through timber construction, 2,000 tons versus the original steel frame specification. The Tustin hangars documented 33 tons of structural steel used versus hundreds of tons the steel design would have required. Construction time: Tillamook Hangar B, 10 months, October 1942 to August 15, 1943. Tillamook Hangar A, 27 working days, July 26 to August 27, 1943. The K-ship fleet. 134 K-class blimps produced by Goodyear Aircraft Corporation, Akron, Ohio. Production peaked at 11 per month in mid-1943. Endurance, up to 48 hours aloft per sortie. K-ships lost to enemy action, 1. K-74, July 18, 1943. Ships lost in blimp-escorted convoys, 0. Submarine threat contained. Axis submarines sank 609 ships totaling 3.1 million gross tons in American coastal waters January-August 1942. Submarine sinkings in American coastal waters by year 454 1942 to 65 1943 to 8 1944. K-74's attack on U-134 contributed directly to the submarine's loss. U-134 was sunk by British aircraft on August 24, 1943, Bay of Biscay. Legacy. Surviving hangars at original sites: Lakehurst, NJ, 2, Moffett, CA, 2, Tillamook, OR, 1. Hangar A destroyed by fire August 22, 1992. Tillamook Hangar B, National Register of Historic Places, listed 1989, currently operates as the Tillamook Air Museum. On September 15, 1945, 2 weeks after the formal Japanese surrender ceremony aboard USS Missouri in Tokyo Bay, Naval Air Station Tillamook was reduced to functional holding status. By October, the last 2 blimps of Squadron ZP-33 had departed for California, their mooring lines released for the last time in that vast Oregon interior. By mid-1946, the Navy had decommissioned every lighter-than-air wing it possessed. The airship era in American naval aviation was over. The hangars remained. They proved more durable than the force they were built to sustain. Over 400 surplus aircraft from theaters across the globe were flown to Tillamook for storage, filling the hangar floors where the K-ships had floated. The Navy abandoned the station entirely in 1948. In the early 1950s, Diamond Lumber moved into Hangar B and began milling Oregon timber inside a structure that had been built from Oregon timber, an industrial circularity that the original engineers, pressed for time and material, would have appreciated. The post-war story of the Tillamook hangars is, in miniature, the story of American industrial capacity after total war. Immense structures, built in emergency, outlasting both the emergency and the institutions that created them. In the spring of 1960, John F. Kennedy, then a senator 8 months from the presidency, stopped at Tillamook during a campaign swing through the Northwest and shook hands with the mill workers inside Hangar B, standing beneath arches designed in wartime Washington by an Armenian immigrant for a task that had already been completed and forgotten. Hangar A burned on August 22, 1992, the 300 truckloads of hay it had been storing for local dairy farmers, providing sufficient fuel to destroy in hours a structure that Pacific weather and wartime urgency had failed to damage in 5 decades. Hangar B stands today at 192 feet, its original timber arches still carrying the loads that Amirikian's equations described in 1941. The 2 layers of corrugated metal sheathing that now cover the original roofing are evidence of the ongoing maintenance that such a structure requires. The arches themselves require no intervention. What that building represents in any year you care to measure from is a principle that the best military engineering always arrives at eventually, that the constraint is not separate from the problem. It is part of the problem, and the engineers who understand that find answers the unconstrained approach would never have generated. A steel hangar built on the original 1940 specification would have housed the same blimps and served the same patrol mission. It would also have taken 18 months to fabricate, through mills already committed to a dozen higher priority programs, and it would have been irrelevant by the time its doors first opened. Amirikian spent 43 years at the Bureau of Yards and Docks before retiring in 1960. 1871 and founding his own engineering practice. He received his doctorate from the Technische Hochschule in Vienna in 1960, submitting a thesis on the theory of protective construction. He was elected to the National Academy of Engineering in 1980. He died in Chevy Chase, Maryland on July 2, 1990 at 91. His citation at the Academy described his contributions in broad terms: shore installations, floating craft, dry docks, innovative construction systems. The wooden hangars, all 17 of them, raised in months from Pacific Northwest timber while the submarines still hunted, are included in the accounting. The Academy noted, with appropriate brevity, that the design had proven itself. The K-ship crews who flew out of those structures for 4 years, holding station above the convoys through North Atlantic squalls and Gulf of Mexico heat and Pacific coastal fog, never saw the arches except from the outside, brief glimpses as they walked the handling line from mooring mast to hangar door. They were inside the gondola by the time the ship was walked into position, already reviewing their navigation charts and patrol assignments, already thinking about what waited beneath the surface beyond the coast. Whatever was below that surface never knew what kept the skies above the convoy full. It was wood, it was catenary geometry, it was a man born in Armenia who understood, at a level few engineers of his generation matched, what an ordinary material could do when the equations were right.